What about the concept of a time invariant system or a time varying system? As in the case of linear system or linearity, which consisted of additivity and homogeneity, we can talk about time invariance or time varying nature of a system from the point of view of a external measurement, or what is normally called the black box approach. You apply an input and observe a response, and on that basis you try to draw some conclusions. So, what do you do with regard to time varying or time invariance property? Well, as the phrase suggests, what we have to do is we have to what is called time shift or time delay, usually in practice, an input. To take a simple example, one may apply to a system a pulse of a certain duration of a particular shape, let us say, starting at some particular instant of time, and then observe the response for some period of time. Then after some time you may again apply the same pulse, that is pulse with the same shape, same width, etc., and observe the response. Now, you are applying in a way the same pulse, in the sense the pulse shape is the same, but you are applying it starting at a different moment of time. So, this is what is meant by a time delay or a time shift. The response, of course, for the shifted or the delayed pulse will begin later, but what you can ask is whether the shape of the response is the same as the previous response, except for the time shift. Now, of course, this can be done with the help of some notation, and it is the idea that is important and not the notation. Given any function of time, say f or f of t, one can talk about its delayed version, and several notations are in use. Since we have already used the letter d to indicate derivative, I cannot use d for delay, but one may use the letter delta for delay. So, delta is the delay operator, and then you have to indicate by how much time interval is the function going to be delayed. So, I could write it as delta with a subscript tau, tau being the time interval operating on f. Now, this produces the delayed function, the function f, which is delayed by an amount tau. To take a specific example, let us say here is the time axis and here is the pulse that I talked about, and let us say it goes from 0 to 1 second. So, this is the function f, as it were, and now if I were to delay it by, let us say, 2 seconds, then the pulse will start here at 2 seconds instead of starting at 0, and then it will last for 1 second as before and go to 0 at 3 seconds. So, this function will be denoted by delta tau f, or in this case, since tau is equal to 1, delta 1 f, that is a function f delayed by 1 second. So, if this is the input, there will be a certain response, then you apply this input and you observe the response. Just as this input is the delayed version of this input, you ask or you try to see whether the response to the delayed input is a delayed version of the response to the original input. If this is so, the system is said to be time invariant, and if it is not so, the system is said to be time varying. Now, this does not require you to know what is inside the black box, what kind of devices, what are the differential equations or algebraic equations or whatever that relate the response and the input variables. It is a test which can be performed externally, so to speak. But on the other hand, as you are already familiar, one can look at the set of equations or the model, and by looking at the form or appearance of the model, one can say something about time invariance or time varying nature of the system. Again, to start with a very simple example, if the relationship between the input u and the output y is simply y is a scaled version of u, y equal to au, then it is not at all difficult to see that this system is time invariant, and of course, the coefficient a is just a constant. Whereas, if I had y t equal to a t into u t, where a t was a function which was not constant, then one can see that the relationship between the input and the output is going to vary with time, and therefore, the system described by this relation is not going to be time invariant. Similarly, if I write down a differential equation, let us say dy equal to ay plus bu, as we have done already, a little argument will show you that if the input is delayed, the response will be delayed, and as in the case of linearity, provided the initial condition is 0 or the initial condition remains the same. That is, the response to an input starting with an initial condition 0 is 1, and response to the delayed input starting with the initial condition after that delay also 0 is another response. Then the response to the delayed input will be the delayed version of the response to the original input. This can be seen by actually making use of the definition of the delay operator and substituting in the differential equation and seeing that this is so. This is because of another property of the derivative, which is a little difficult to talk about, although it is not very difficult to see, and that is the following. That is, if I have a graph here like this, let us say, and if I shift the graph by a certain amount, then the derivatives also get shifted by the same amount. That is, shifting the graph horizontally along the t-axis does not change the derivative values, it only changes the instance of time at which the various values are taken by the derivative. Of course, the shape of the wave or the function remains the same. So, this is a property of differentiation, that differentiation is invariant with respect to time shift, or to use a more sophisticated word, translation in time. So much for time varying or time invariant and linear or nonlinear systems. And as I said earlier, the method of Laplace transformation and therefore the S domain methods using that, such as the root locus method, the Routh criterion or test or for stability or location of roots of a polynomial, and the frequency domain methods such as the method based on Bode plots, Nyquist criterion, Nichols charts, etc., are not applicable for systems which are nonlinear, that is, which are not linear, or for systems which are time varying or not time invariant. Now, of course, as I told you earlier, nonlinear systems and even time varying systems do occur in nature and in engineering practice. The pendulum, whose swing is not sufficiently small, or in fact for no amount of swing, is the pendulum exactly described by a linear differential equation. So, it is a nonlinear system. The fly ball governor would be another example of a system where there would be a nonlinearity. Now, for quite some time people tried to work with the nonlinear models, and to a limited extent they could do some work. One method of handling a nonlinear model or a time varying model was to approximate it by a linear model or by a time invariant model. In the case of nonlinear systems, when they are approximated by a linear model, the process is known as linearization. Now, of course, this only results in an approximation, and unfortunately one may not be able to know or say much about how good the approximation is. This is one of the major problems which persists even today. In fact, the nonlinear model of the system itself is an approximation to the actual behavior of the system, because you may have neglected so many things, you may have assumed that some things remain constant and so on. So, the physical system is one thing, the nonlinear model of it is only a model, that is, it is only an approximation to describe the behavior of the system. And then the nonlinear model now you want to replace by a linearized version. So, there is a further degree of approximation, and unfortunately it is not always very easy to find out how good or how bad the approximation is. However, so it was not as if the things were that hopeless. In fact, around 1900 a Russian mathematician by name Liapunov did some work on nonlinear systems, and essentially those were systems which also involved inputs, that is, therefore his work was applicable to nonlinear control systems. He introduced an approach or a method which is known as the Liapunov method or Liapunov approach, and he showed that under certain conditions, if you replace a nonlinear system by an appropriate linearization and then study the stability properties of the linearized system, you can infer something about the original nonlinear system. And he introduced a function which has become known as a Liapunov function after him, and there was a lot of work which was done at that early time, but it was done in Russia. The language of the work of course was French. Somehow it did not catch the attention of people, and therefore not much progress took place following the Liapunov approach till the late 1950s, when people, realizing that you could no longer make approximations or no longer could only work with linear systems, went back to the problem of nonlinear or time varying differential equations and rediscovered or discovered the work of Liapunov and made a bit of progress using the Liapunov approach or the Liapunov method. So this was the kind of thing that led to a reconsideration of the differential equations that describe the system rather than transfer functions or frequency response ideas. In particular, if the differential equations were linear, then the matters became easier to deal with, and one could deal with linear differential equations with constant coefficients without using the Laplace transformation, and such methods became known as time domain methods. So these sort of started being studied from the 1950s, time domain methods for control systems, not just single input, single output control systems, but multi input, multi output control systems, to be modeled by differential equations rather than by transfer functions or through frequency response, even though the system may be linear and time invariant. There are some things that you can do without using the concept of the Laplace transform or transfer function and the ideas of frequency response, and there are some advantages in doing that. They are also in a way more direct or simple once you have understood or mastered the required mathematics. I gave you an example of such a system already, namely writing it in the vector notation dy equals ay plus bu, where y is not a single variable, but it is a vector of several variables, say y1, y2, yn. So there may be n different variables, not just one response variable, and u may be a single input. In this case, the notation I have used is such that u is a single input, but again u can be a vector input, that is, the system can have more than one input. A is a matrix of coefficients a11, a12 and so on, and B is a constant vector, again involving a number of components. Now such a system of equations which made their appearance and began to be studied and used as the model starting with the 1950s are known as state variable equations, and such a model is known as a state variable model. In fact, usually what happens is the y that I have talked about, as I told you, the letter y in control theory practice is usually limited for an output, u for an input. Then what is this state variable? These state variables will not be either input, they may be an output variable or they may not be an output variable. We do not have time to go into these details. Usually your textbook will have a chapter on state variable formulation of system equations and in particular of control equations, so you should take a look at that. In that case, the state variables will be a set of variables x. Again, this may be more than one, so this is a vector. The input variable u may be one or more, the output variable y may also be one or more variables, and the state variable equation model, which is very commonly used, is then dx equal to ax plus bu. D denotes the differentiation operation, A is a matrix, B is a matrix. In general, the output vector, as it is called, y, is related to x and u through an equation like this. So, this pair of equations is referred to as a state variable set of equations. These are known as the state equations, and this set of equations is known as the output equations. So, this is the kind of model that one can start with instead of starting with transfer function or frequency response ideas. In fact, if you recall, when we started our discussion of the DC shunt motor driving the load, the simplest load that we talked about, we in fact wrote down differential equations. Of course, in the beginning we said let us consider the operation of the motor in the steady state. So, the current is constant, voltage is constant, torque is constant, speed is constant. In that case, there are only algebraic equations that relate the various quantities. But since we are interested in the transient behavior, what happens when the motor is switched on, or the load changes suddenly, or the supply voltage changes suddenly, we have to write down the differential equations for the system, and this we did. And let me recall them. The armature circuit of the motor gave rise to the equation EA of t, and now I am writing as a function of time explicitly to allow for the fact that the armature voltage may vary. So, this equals the back EMF, which is kb into omega t now, because the speed also may vary with time, plus the two terms which are Ra Ia of t, the armature resistance drop, plus the term due to the inductance of the armature La dia dt. Now, already there is a derivative of the current appearing here. So, we have a differential equation. The second equation, the torque equation or the mechanical circuit equation, is also a differential equation. The generated torque, the torque produced by the motor, Kt into Ia of t, part of it is used to overcome the load torque. So, I am writing it as TL of t, and a part to overcome the moment of inertia. So, J d omega dt, and a part to overcome the viscous friction. So, Kf into omega. So, the derivative of the speed also makes an appearance here. And in fact, it is not difficult to rewrite these two equations in such a way that they appear in the so called state variable form. What will be the state variables? As you can see, armature current derivative appears in one equation, speed derivative occurs in the other equation. So, we could choose as state variables x, let us say I write down the speed first, omega and Ia. So, the two state variables for our control system will consist of the two variables omega and Ia. X is sometimes referred to as the state vector. So, we say that the state vector has two components and is made up of the motor speed and the armature current. I will leave it to you to rewrite these two equations so that they look like dx equal to ax plus bu, but what is going to be u in this case? Now, if you look at the armature equation, the armature voltage appears there, and if you look at the mechanical equation, the load torque appears there, in addition to terms involving Ia and omega. Therefore, we can choose as the input u the vector consisting of the applied armature voltage and the load torque. So, our u will consist of two variables Ea and TL. With this, then you should rewrite these two equations so that they look like dx, that is d omega dt and dia dt, equal to a matrix multiplying omega and Ia plus another matrix multiplying Ea and TL. So, find out what those two matrices A and B will be for this problem. Sometimes these two Ea and TL may be kept separate, in the sense Ea is an input variable in a way, because this is providing the power to the drive, whereas the TL, as we saw earlier, is more thought of as a disturbance variable. That is, the uncertainty in TL is likely to cause changes in speed, whereas the power supply voltage can perhaps be maintained reasonably constant. You want the drive to function in spite of load torque variation. Therefore, this, instead of taking them together as one single vector, you may split it into two parts. In that case, the part that corresponds to the disturbance is usually denoted by the symbol W, and so the equation may look like dx equal to ax once again plus bu, and now I need one more letter, and so EW. So, x is the state vector, u is the input vector, w is the disturbance input vector or the disturbance vector. And what about the output equation, y equal to Cx plus du in this case, and of course the disturbance may make its appearance in the output equation as well. What will be the output variable for our problem? Well, basically we are only interested in omega, we are not interested in Ia. So, the output variable will be simply omega, and therefore y will not be a vector really, but a single variable omega can be written as Cx. So, that is easy, 1 0 omega Ia. So, 1 into omega gives omega, 0 into Ia gives 0. So, I have omega equal to omega plus nothing, therefore, d is equal to 0 and f is equal to 0. Find out what these matrices A, B and E would be if I treat the load torque as a disturbance variable separately from the armature voltage as an input variable. So, we can write down the equations for the motor control problem in the state variable form or as a set of state variable equations, state equations and output equations, and then start our study from these equations and not apply the method of the Laplace transformation, that is, as we did earlier, take the Laplace transformation of both sides, that is functions on both sides of each equation, then make use of properties of the Laplace transformation, then make some manipulations and finally get something like a transfer function and so on. That is certainly possible in this case, and because the number of state variables may be more than one, the number of inputs may be more than one, the number of outputs may be more than one, instead of just a transfer function or two transfer functions as we had earlier, one transfer function relating the applied armature voltage, the other transfer function relating the load torque to the speed of the motor. In general, we will have what are called transfer function matrices, that is, we will have a matrix whose entries are transfer functions. So, there is more than one transfer function because there is more than one state variable or output variable and more than one input or disturbance variable. Now, of course, that is one way of handling the problem, that is, just write down the equations and then apply the Laplace transformation and get back to the S domain and then use the ideas of the S domain. Of course, it was tempting to do that because the method of Laplace transformation had already been worked out for, say, a single input, single output with a single state variable, as we saw earlier, that kind of a system. But then this is not really a time domain method, it is a transform domain method or a S domain method. And of course, ideas which were derived for the single input, single output case could be extended to such cases. But what about time domain methods only, that is, no Laplace transformation will be used, and we will not assume that the input u or the disturbance w is a sinusoidal function. What can we say about such a system? Now, as I said, it is possible to say something, it is possible to in fact say quite a lot, it is possible to find out various things about the system, explore properties like stability of the system and so on. Of course, this requires new concepts, and these new concepts, as you can guess, are going to be somewhat related to the kind of model that we have, namely we have matrices, and therefore, a lot of matrix theory becomes applicable here. Matrix theory had been introduced earlier, we referred to it to some extent when we talked about the signal flow graph and determinants and so on. Matrices are used in that connection, they were already being used. Now, they are going to be used in the context of differential equations. So, when a lot of matrix theory results have been developed or are available, one can use them to apply to linear differential equations in the state variable form. Now, before we proceed further with our motor control problem now in the time domain formulation, let us just briefly take a look at the following. What I have written down in the matrix form is only for a linear system. The matrices A, B, etc. may not be constant matrices, that is, they may have functions which change with time, therefore, it can represent linear time varying systems as well, but linear systems. However, one can think of differential equation representation of nonlinear systems and even time varying systems, and a fairly general way of doing that is as follows. Symbolically I will write x dot or the same as dx equals f of x, u, maybe w and t. What do we mean by this? X once again is a vector consisting of several state variables, u is a vector consisting of several input variables, similarly w or disturbance variables. What is this f? Well, this f stands for a vector of functions, not just one function. So, in other words, this just represents compactly a whole set of differential equations as follows. X1 dot, let us say the first state variable, its derivative is a function f1 of all the state variables perhaps x1 to xn, all the inputs variables u1 to up perhaps, all the disturbance variables say w1 to wq, and also a function of time itself. This is what is meant by the function f1. Similarly, x2 dot will be equal to a function f2 of all these variables and so on. Now, these functions f1, f2, f3 etc. put together constitute the vector f. So, this is a more general formulation, state variable formulation of a system which could be nonlinear, because this function f1 there is no restriction put on it. So, the system could be nonlinear, t appears here explicitly. So, the system could be time varying, and therefore, as you can expect, a large number of systems can be represented by a set of first order differential equations like this. So, this is the state variable formulation for a large number of systems, the systems which may be nonlinear, systems which may be time varying. Of course, writing the description is one thing, then being able to get some information out of it, being able to solve them is a different thing. And as you can expect, solving of nonlinear systems or time varying systems, or getting some conclusions or finding some results about nonlinear or time varying systems is not going to be easy, because we do not have any longer matrices. A number of the results from matrix theory are no longer applicable. So, some new techniques have to be developed and so on. And these techniques were developed because already mathematicians had been looking at this kind of a problem, not a control problem, but the problem of solution of differential equations for a long time, and had developed some methods which then became or could be applied to our control problem. Of course, all this is for what may be called lumped parameter systems, because we have only ordinary differential equations. There is only one independent variable t, there are finite number of state variables x1, x2, xn, or whatever number they are, lumped parameter systems. Our motor is an example, motor control system is an example of a lumped parameter system, in the sense we are looking only at two state variables, speed, armature current, and we are having only ordinary differential equations. I mentioned to you earlier that one can encounter what are called distributed parameter systems, that is, systems which are extended in space and cannot be considered to be lumped. A resistor or an inductor, for that matter, is also distributed in space, but a resistor is represented by a simple relation like V equal to Ri, terminal voltage V, current I. Similarly, an inductor is distributed in space, but we can represent it by a differential equation like voltage equal to L di dt. Now, of course, this representation ignores the distributed nature of the inductor, but in many field problems we cannot neglect this variation in space or over space region. In many problems arising in process control, problems of heat transfer, mass transfer, problems involving flow of fluids and so on, things vary in time, they vary also in space, or in other words, the space variables are also equally important. Therefore, you just do not have one independent variable t, you have additional independent variables, and as a result the differential equations that you get are not ordinary differential equations, but they are partial differential equations. The subject of partial differential equations, as you can expect, is more difficult than the subject of ordinary differential equations, but one could talk about a similar kind of formulation for partial differential equations as well, although it is not as general as one may want it to be. Let me illustrate the time domain method for our motor control problem. I will not be able to go into full details, but I just want you to get an idea of what exactly is involved and how the time domain approach will differ from the S domain or the frequency domain approach. So, we have a pair of differential equations describing the control system, and they could be rewritten in the state variable form. Now, there is one way of handling the equations in the state variable form, which, as I said, involves a lot of results from matrix theory. I will indicate them to you a little later after we look at a somewhat simpler approach. Now, here are the two differential equations which involve armature current and the motor speed omega. The variable of interest to us, of course, is the motor speed omega. So, a natural thing to think of is to eliminate the armature current. In fact, for the steady state equations, this is exactly what we did earlier, to find out the relationship between steady state motor speed, load torque and applied voltage. The armature current was not of particular importance, although it was relevant because the armature current should not become very large and things like that. Now, something similar can be done with the differential equations, that is, from these two differential equations we can eliminate the variable IA, the armature current, and then what is going to happen? As you can expect, we will get a second order differential equation for the speed omega. I am not going to find out what that equation is going to be. You should try to carry out this elimination for yourself and get the second order differential equation. The elimination is not going to be that straightforward because each equation has both omega and IA in it. So, here is the equation which has derivative of current, but it has both speed and armature current. Here is the second equation which has derivative of speed, but it also has the two terms armature current and motor speed. Therefore, the elimination is not that simple, but it is possible. And after the elimination, one could obtain the following type of or kind of equation. As I said, it is going to be a second order differential equation. So, what will it look like? It will look like d square omega, the second order derivative makes its appearance, plus a coefficient, let us say a1 times d omega plus a0 times omega. This is the kind of thing that we will have when we have eliminated omega. What happens to the input terms? We have the input EA, the armature voltage, and the load torque TL. Now, what is going to happen in general is that when we eliminate the variable IA, derivatives of these two input variables may also appear, and so we may have a set of terms like this B1 into derivative of EA plus B0 into EA plus C1 into the derivative of the load torque plus C0 into the load torque. So, on the left hand side I have the variable omega and its first and second derivative. On the right hand side I have the input variable EA and its first derivative, and the disturbance variable TL and its first derivative. So, this is the kind of differential equation that I get, and of course, we had looked at such a differential equation earlier when we got introduced to the method of Laplace transformation. At that time we talked about several parts of the solution or response omega, namely the one that corresponds to 0 input or 0 initial conditions and so on. Now, we can talk about this equation in exactly the same way, although the method of solution need not be the one based on the Laplace transformation. And in fact, we had seen a method of solving a differential equation without involving Laplace transforms. So, let us assume for the moment that we are looking only at the part of the response that will remain when the applied voltage is 0 and the load torque is 0. For example, the motor has been running for some time and then you suddenly change EA to 0 and you suddenly change the load torque to 0. That is, there is no longer any load and there is no longer any power supply, but still the motor was running. Therefore, because of its momentum, it will keep on running for some time. So, imagine that we are studying the motor under that condition. Therefore, the right hand side will become equal to 0. And then, as we saw earlier, the equation can be rewritten as d square plus a1d plus a0 acting on omega equal to 0. That is, we have an operator acting on omega equal to 0. what was this operator called? It was called a polynomial differential operator. In this case, the operator is of degree 2. So, what was the way of finding the solution of this? The way was to factorize this polynomial differential operator and then make use of certain basic facts like the exponential function satisfies a simple first order differential equation and so on. And then as we saw, the nature or the factors of this or the roots of the equation corresponding to this determined the behavior or the nature of the response. So, the corresponding equation as it were would be d square plus a1d plus a0. If you looked at this as an algebraic expression and try to find out the roots of this equation, if the roots of this equation were, let us say, lambda 1 and lambda 2, then the solution omega t could be written as k1 e raised to lambda 1 t plus k2 e raised to lambda 2 t. This equation of course could be called the characteristic equation, or since of course there is an operator d, what I mean is an algebraic equation. So, think of d as just an algebraic variable. So, the roots of this equation are lambda 1, lambda 2. They are called the characteristic values, or another term that I had introduced at that time was eigenvalues, and the solution therefore looks like this. In other words, when the motor voltage is switched off, the load torque is made to 0, the variation of motor speed will obey a law like this. Of course, it may happen that the variables lambda 1, lambda 2 are not, the eigenvalues lambda 1, lambda 2 are not real numbers, but they are complex numbers. We have looked at those kinds of things earlier, but the nature of the solution is given by this. And so, we saw that if lambda 1 and lambda 2 have negative real parts or they are negative real, then this will go to 0 as t tends to infinity. So, there will be no problem with the motor racing away, that is its speed increasing, in theory indefinitely, in practice becoming very high. That depends on the nature of the eigenvalues, which in turn depends upon the equation d square plus a1d plus a0 equal to 0. Now, if we could change this equation in some way, then we would be able to change the behavior of the motor. For example, this goes to 0, but not fast enough. The time constant of the motor is not small enough. So, the motor slows down, but not rapidly enough. We may want the motor to come to a standstill as quickly as possible, because in the other direction, when the motor is turned on, the motor will pick up the speed perhaps very rapidly. So, we may want to change the time constants associated with the motor, change lambda 1, lambda 2, therefore change a1 and a0. But how can we do that? Our differential equation is given like this. So, what is it that we can change? Now, this is where we can use some of the ideas from feedback theory that we have studied earlier, namely proportional feedback, derivative feedback, integral feedback and so on. Well, we have the input variable EA now, and of course, the input variable EA we had put equal to 0. But now, as in the case of feedback, we could have the input variable coming from not just the applied armature voltage or the reference voltage, but coming from a difference of two signals. One was the reference voltage, let us say RT, and the other was the signal obtained as feedback based on the speed, and this difference could be then EA of t. So, EA of t could be RT minus this feedback signal, and even if RT is set equal to 0, the feedback signal is still there, and therefore, although the external voltage is reduced to 0, internally to the motor the applied voltage is not going to be necessarily 0. So, in other words, we can express EA as say RT R minus, what did we have earlier? We had the k tacho generator omega. Of course, there was a gain k that we had introduced, because this difference may be small enough, and therefore, we really had EA equal to k, the gain of the amplifier, multiplying R minus k tacho generator omega. So, this is what one may think of doing. Now, if you take the differential equation that we had here, this one, and now EA is going to be replaced by, or EA is going to be obtained as k times R minus k tacho generator omega, you will see that because there is this multiple of EA here, there will be a multiple of omega which will be introduced on the right hand side. Because there is a derivative of EA and a multiple of it here, the derivative of omega also will appear on the right hand side. Of course, in addition r and dr will appear on the right hand side. So, what is going to happen is, and I am going to show it only symbolically, I am not going to write down the exact expressions. We have on the left hand side d square omega plus a1 d omega plus a0 omega. So, I am just going to write all that stuff as simply this operator acting on omega equal to, what will happen is, now because of the feedback Ea involving omega, there will be now a term which has d omega on the right hand side, there will be a term which has omega on the right hand side, plus there will be a term involving dr, another one involving r, and then as before the torque terms dTL and TL. So, with feedback, and what kind of a feedback it is? It is proportional feedback, because we are taking a multiple of the variable omega as the feedback signal, and then taking the difference between the reference signal and this and amplifying it to generate the applied voltage, armature voltage Ea. So, this is what the equation is going to look like. And now we can set once again r equal to 0, TL equal to 0, that is the external voltage is made 0, the load torque is reduced to 0. What will happen? Now, we have these additional terms on the right hand side, and of course, we can transfer these terms to the left hand side. Therefore, the left hand side now with this change made will look like d square as before, but not a1, but a1 prime d or a1 dash d, that is the coefficient a1 will change, plus not a0 any longer, but a0 dash omega equal to 0. So, what is it that we would have done in this case? We have changed the operator from d square plus a1 d plus a0 to d square plus a1 dash d plus a0 dash. And how has this change taken place? This change has taken place through the proportional feedback. Now, what this a1 dash will be and a0 dash in terms of a1 and a0 and the feedback equation, the tachogenerator coefficient and the gain of the amplifier, it will depend on all of these. And I would like you to work out the exact expressions for a1 prime and a0 prime in terms of the old coefficients a1, a0 and the parameters of the feedback, namely the tachogenerator coefficient and the gain of the amplifier k. But the point is that the differential equation is changed, the characteristic equation is changed, and therefore the solution of the equation will also change. We expect therefore that the eigenvalues will have changed. The solution may still go to 0 as t tends to infinity, but it will do in a different way at a different rate. And so, we can now pose the problem, well, is it possible by using this feedback, choosing k tachogenerator and the gain k, to change a1, a0 in such a way that the behavior of the system is improved, the response of the system is changed to what we want. Originally, the time constants may have been large, typically one of them is large, the other one may not be so large. We want to reduce them. Can it be done? We can also ask whether the system can become unstable by means of this feedback. That is, the roots of this may become such that they have a positive real part or they become purely imaginary. So, the system response becomes oscillatory or even tends to grow exponentially. Can that happen? The answer in this case is no. As we saw earlier, proportional feedback using the method of Laplace transform and transfer function we saw and the root locus approach, that there will not be any instability, but there could be oscillations, there could be oscillatory behavior of the system, but damped oscillations. You can check using this approach that can happen. In this approach, of course, I have not taken Laplace transforms anywhere. I am only looking at the characteristic equation of the system. Then I know the fact that if I factorize the characteristic equation, certain coefficients or eigenvalues appear and they determine the nature of the response of the system. I am making use of that and answering questions which we had looked at and answered earlier using the method of the Laplace transformation. So, this is something I would like you to carry out for yourself, and this is an example of a time domain method. Now, this is about proportional feedback. What about derivative feedback? Can we use derivative feedback? What about integral feedback? Can we use integral feedback? And as you can see, the things are not going to be very different from as far as the computations or the work is concerned. Of course, the result will be different. So, for example, suppose I want to introduce integral feedback, then what did we do? Well, we introduced the integrator after the output of the difference device. So, here is R, here is the feedback signal which is k tacho generator omega, here was the difference signal, and then we had k divided by s when we use the transfer function notation. This was the integrator. Now, therefore, what is it that I am doing? I do not want to use s variable anymore, because I am not thinking of Laplace transformation, I am thinking of an operation of integration. So, what should we do? Well, let us call this, once again this is still the motor armature voltage EA. Let us call this variable, we have to give it some other name, let us call this variable E as it is traditionally done. Now, of course, in terms of transfer function, EA of s is 1 k by s into E of s. But what about as functions of time? What is the relationship between E and EA? EA is the integral of E, and therefore, the derivative of EA is E. So, dEA is E. So, this error signal E or the difference signal E is the derivative of the output of the integrator. The output of the integrator is the integral of the input of the integrator is the derivative of the output. Therefore, this is the relationship that holds dEA equal to E. E itself, as before, consists of, in this case of course, I have this factor k. So, I have to be careful here, I have to write here d of, what will it be? dEA equal to ke. E will be equal to R minus k tacho generator omega. So, go back to the second order differential equation describing the behavior of the motor or the speed of the motor, in which EA and the load torque terms appeared, and now make use of this fact that we have E equal to R minus k tacho generator omega, dEA is equal to ke. Now, we have to eliminate the variable EA, or we cannot any longer set the variable EA equal to 0. So, we have to do some further manipulations, and the nature of the system or the differential equation coefficients will be changed by the presence of this coefficient k and by this operation of integration, which of course here appears like a differentiation, because I am writing the derivative of the output equal to the input rather than the output equal to the integral of the input. So, just as proportional feedback change the differential equation coefficients, integral feedback will also change the coefficients of the equation, or it may even change the order of the equation. And in fact, this is exactly what happens. Why do I say so? When we looked at the root locus method, what did happen in that case? This S introduced an additional pole in the transfer function. So, instead of 2 poles, we had 3 poles. As a result of it, the root locus changed and stability properties also change. So, what is going to happen here is, in this case, when we do this, the differential equation will no longer be of second order in omega, but the differential equation will be of third order in omega. We would like to eliminate the variable EA, set R equal to 0 finally, set TL equal to 0. So, obtain that differential equation, check for yourself that it is a differential equation of third order. So, the order of the system goes up by 1. So, we will have more coefficients now, but again we can factorize the characteristic equation, look at the eigenvalues, see whether they all have negative real parts or not, and so on and so forth. So, this is something I would like you to do, and then we will complete this example as an illustration of one approach, one time domain approach. The other time domain approach will involve some matrix theory and some matrix manipulations. So, I will not be able to go into great detail as far as that other approach is concerned.